Okay, so we're going to be talking about logistic regression. And logistic regression is when you have dichotomous outcomes. Dichotomous meaning, um, whoops, meaning one, two categories as an outcome. So let's take a look at logistic regression and how it works. So in ordinary least squares regression, or in a GLM, which is what we've all been learning about so far this year, your y hat, which is your expected score, was always an indicator, or always indicated a predicted score on your outcome variable, or a predicted value on whatever your outcome is. Remember, the goal of regression, or the goal of a GLM, is to come up with one expected score for every person, combination of x's. Now in logistic regression, you're still going to get a y hat. You're still going to get a predicted score, but unlike what you'd think, you would think it should be 0 or 1 because our outcome that we're interested in is a 0 or 1, like a yes-no sort of outcome. But your y hat is not a 0 or 1. What it actually is some number between 0 and 1. And it's helpful to think about it as a probability that y equals 1. Sometimes people call that probability of an event. So in some of the readings that I gave you, they'll call this the probability of an event. An event just means y equals 1. What could be a good event? The probability that I got an invitation to the Grammy Awards. That would be y equals 1 if I got an invitation to the Grammys. Maybe one day. All right, so it's the equation that you're going to look at. The equation is the probability that y equals 1. And it's written like this, which you may remember from intro stats. Probability y equals 1. And when you're predicting it from an x, it's the probability y equals 1 given x. That's what this little pipe guy means, given. So the probability that an event will happen, the probability I will get invited to the Grammys this year is 0. The probability I will get invited to the Grammys this year, given that my cousin was nominated for a Grammy, that's not true, but just I was coming up with it would be higher. Okay. So for continuous outcomes, this is what you're used to looking at. You're used to looking at straight lines. So you've got a predictor, an x, and you've got a predicted value for y at every value of x. And mostly they fall on this straight line, except for when we did nonlinear models, and then they fell on a different line that was not straight. For a binary outcome, the line representing the probability of an event, or the probability of 1, given a score of x, looks like this. It looks like a little s. So if you have a really good predictor of your y, then if a person has a really low score on your predicted x, they have a very low probability of this event happening. Now when x is high, if you have a good predictor x and x is high, then the probability is 1 or 100% that they will get a 1 on the outcome. So here, your predictor x in that ridiculous idea I just came up with is number of Grammy nominations. With 0 Grammy nominations, it's pretty likely that 0 is whether you'll get an invitation to the Grammys. And with a lot of nominations, you're almost certainly going to be invited to the Grammys. That would be a pretty good predictor. So that line isn't straight. That line that looks like an S is something called a log function. And the equation for simple logistic regression involves this log function. It's analogous to the predicted y equals b0 plus b1 times x in linear regression, but it looks like this. This is the equation for the slope of that function. The equation for that line, that function. It looks like this. You'll see some familiar looking numbers or figures in here, like a b0 and a b1 times x. So just to reiterate some symbols that I've shown you before, P is probability, hat P is predicted probability. Ln is the natural log, or the logarithm with base e. E is this irrational number, which is about 2.78. So through algebra, we can solve for this predicted probability. So the predicted probability is equal to 1 over the rest of this equation, which, look at this, b0 plus bx times plus b1 times x1 looks real familiar. Okay, so b0 is just like the linear regression intercept. So the linear regression intercept here is about at 1. And here is the same idea. It's just that this curve is not straight. It's a logit curve. So B0 defines the height of the curve. Stick with me, my story gets better. Gosh, I think I'm funny sometimes. Okay, so your data don't fit a line, so we're estimating probabilities. But you can use a logit transformation to calculate the log odds, and then that becomes a line, which is how we're able to fit something that's kind of like straight lines within this model. Somebody thought of that, and that just makes me so happy. How cool is that somebody was like, I know. Let's just use a logit transformation. Amazing. All right, so if this is, this is just example data to give you an idea of what things look like. Here's a predictor, an X. Here are my observed values. Each one of these dots is observed. This is a probability that the outcome equals 1. In this case, it's probability of owning that Justin Bieber album. This is in the Justin Bieber paper that I gave you to read. So essentially, they're saying here is a good predictor. If you take this equation and you use a logit transformation, it's actually a straight line. It's so cool. And it's a straight line. It works the same way that it did before, where you have a 1 unit increase in x and have a b increase in y. All right, when would we want to use a logistic regression? You need to use a logistic regression anytime you have an outcome that's dichotomous. So that's an outcome with 2 categories. But questions about logistic regression, I didn't do my vocal warm-ups before class today. The questions are asked in the same way that they would be for a linear regression equation. So the questions don't sound very different. It's just that instead of saying, does X predict Y, you would say, does X predict the probability of Y happening? Okay, so I have this a little bit, I have this example we're going to walk through. So we're going to say that you've gone to some sort of event or gathering, maybe like a conference, and there are a bunch of professors there. And you've got professors from 2 different Ohio colleges and universities. You've got Kenyon College represented. They're up in Gambier, Ohio, a little private university. And then you have Ohio State University. Now, just for imagination, we're going to pretend that they all have color-coded name tags so you can tell on site whether someone's from one of those universities or not. Now, if you want to talk to people who have tenure, maybe you're looking at wanting to do a survey of people who have tenure. For some reason, you want to talk to people who have tenure. So I'm going to have 2 pieces of information. I'm going to have whether the people are from Kenyon College or from the Ohio State University, and I have whether the person has tenure or doesn't have tenure. And you got the list of people in advance, and you have some numbers. So here are the basics. It's a 2x2 table. I have whether the person is at Kenyon or whether the person's at Ohio State. Did the person have tenure or do they not have tenure? So this is my 2x2 contingency table, which I think you've seen a lot before. Essentially, I have a total of 421 professors. And so if I grab a random person and talk to them, well, not grab, if I say, excuse me, sir, to a random person, it's more likely that that person will be from Ohio State than from Kenyon College. I tap someone on the back. I can't see their name tag. They turn around. They have a name tag. Now I know which university they're from. You're also, no matter who you tap on the back, you're equally likely to talk to someone who has tenure and someone who doesn't have tenure. About equally likely. So, in this sample, is having tenure related to where the person works? What do you think? I got a couple of thumbs ups. Or, to phrase it another way, if I wanted to talk to someone with tenure, would I have a better chance if I randomly picked someone from Kenyon or randomly picked someone from Ohio State? I think that the numbers bear out here that if I want to talk to someone with tenure, I'm much better off guessing that's someone from Ohio State. But that's not a significance test. It's just my raw numbers. So if I want to phrase this as a logistic regression question, you would say, I want to predict tenure status from whether a person works at Ohio State. So now you've seen this before, I think, yes? You've seen things like this before, 2x2 table? Learned about maybe chi-squares or percent exact agreement, something like that before? So there are other ways to analyze data that look like this. A 2x2 table is just scratching the surface a very long time ago. So you may have learned other ways to do this, but like in other modules that I've introduced to you, we're starting with a really simple example so that you understand a little bit easier how this works. And then using that math, you'll be able to add other components to it. So eventually we can add lots and lots of predictors, just like we could with a regular GLM. So, like the GLM, logistic regression works based on model comparisons. Remember, all of this is about reducing error in our model. So the first thing that we're going to do with a logistic regression is we're going to get an unconditional model. So that unconditional model will estimate the probability of an event happening, or probability of getting a 1, if we've got no predictors in the model. Just like before, do you remember we called that the unconditional model or the grand mean model? If we just guess the mean for everybody. This is the same idea. So second, we'll get information on the conditional model. So that's the model where we have, we're going to estimate the probability of getting a 1 or of an event happening given the predictors in the model. Given predictors in the model. And that's akin to our other conditional models like we've used before. So the SPSS code to run logistic regression is pretty simple. This is what it looks like. I've got variables. My outcome is tenure, and I'm going to enter the variable Ohio State, OSU. These are what the variables are called. I did not introduce them to you in advance. I apologize. But that's what they're called. So we're going to start with for some reason they call this grand mean model or the unconditional model step 0, which I guess that makes sense. 0 predictors in the model. That's what it's called. So when you go into the logistic regression output, you'll get a couple of pieces of information right away. First, you get an N. So always a good policy to check and make sure that your N matches the N you were expecting. And then you get this same thing that you got in all of your ANOVAs, which is checking to make sure that this value that you think represents 1 matches up to the way that the computer program has decided to code 1 versus 0. Because this is our outcome, dependent variable encoding. Very important that we know which direction that goes. Okay, now we're in the logistic regression output. eventually, we're going to get a B0 and a B1 from this equation right here that we just derived earlier. But within this grand mean model, we don't have any x's. And so we are looking at the intercept only model, or this probability right here. So I'm going to go through what we get here in block 0, which is our unconditional model, to sort of show you where all these numbers come from. Okay, so we're going to get a y hat. And the y hat, again, is the probability that each person will get a 1 on the outcome. And that means that person has tenure. We're completely ignoring the predictor. It's like it doesn't even exist right now. Now right here, you'll see there's this little guy right here that says cut value. The cut value equals 0.5. So basically what we're saying is if the probability, the y hat, the probability is less than 0.5, we expect that that person does not have tenure, that they will not have the event. But if the y hat is above 0.5, then we do expect that they have tenure. We do expect that the event will happen. So this little classification table is pretty useful to determine whether your equation's doing a good job of detecting where people should be. Right now, what's happening is that once I have solved this equation right here, I end up with a y hat for every single person above 0.5. Because every single person we're predicting has tenure. We're predicting that the event happens. So that's what this cut value is and how that corresponds to this table. If I've done a really good job predicting people, I'll have people both above and below that cut point. But right now, I don't have any predictors in the model, so we're just saying there's more people who have tenure than don't, so we're going to put everybody in the yes column. Okay. Here is that equation. So to get the y hat for everyone, to show you where that number comes from, this cut value, the number that you compare to the cut value comes from, you're going to take the B0 and you put it into this equation. And that means that the y hat, if I've solved this correctly, which I'm pretty sure I have, the y hat is equal to 0.506 for every single case. Do you remember in the grand mean model in the GLM, the y hat for everyone was the mean? Here, the y hat for everyone is basically the proportion of the sample that has the event happen. So my y hat for everyone is 0.506. Just slightly more people have tenure than don't. So we're going to end up expecting that everyone has the event happen. That's what I just said, because y hat's greater than 0.5, it means everyone will be classified as 1. So the other thing that you end up here with is this contingency table. So you'll see that of all of the people who did not have tenure, we expected that they all did have tenure, so we got none of them correct. We got 100% of these guys correct, though. On average, we got 50.6% correct. Look at that, 50.6. You see that? 50.6. Math. Ta-da. With the empty model, we're still going to get a coefficients box. It's not very useful. I'll just show you what the numbers are. This B is the logit, which I explained on the couple of slides ago, what the logit is and how that works. Instead of a t-test, you get a walled test, but it essentially functions in the same way. I'm not going to make you memorize how the walled test is different than the t-test. Suffice it to say, it's a significance test that works really well when you have data that are non-normalized data. So you also are going to get a p-value for this in the same way that you would for a t-test that you're used to. This is telling us that this coefficient is not significantly different from 0. It's real small. The walled statistic is calculated exactly like the t, which is the b divided by standard error squared. It's fine. That's where those numbers come from. So let's talk a little bit about this exponent b over here. This guy is new. We have not seen him before. We've seen b's, we've seen standard errors, but now we're going to talk about the exponent b. This is the odds ratio. So this is the odds of having tenure, which is 1, that goes in the numerator, over the odds of not having tenure, which goes in the denominator. So the odds of having tenure are 1.024 times the odds of not having tenure. And when the odds are the same, then they're about 1. So a probability of 50% is about the same as a odds ratio, which is what this is called, the odds of the event happening over the event not happening, of 1. Okay, so that's all sort of the baseline of the grand mean model, essentially. So now we're going to move on to block 1. It's the good stuff. It's where we put in our predictors. Let's see what's happening. So we have these 3 different omnibus tests of model coefficients. And this is basically testing whether we've done a good job reducing the error in our model with the things we've entered in this step, this block, and this model. Now, I'm not going to distinguish much between the step, the block, and the model, but there are different ways that you can add in variables or predictors in different waves or orders in order to try to test whether some of them are more effective at reducing error than others. But the one that will be useful, they'll all be the same. If you do everything in one step, they'll all be the same, so it doesn't really matter to distinguish between them. But essentially here, the model, we're saying how much better does this model fit now. A significant predictor here, a significant value of the chi-squared here means we've done a good job improving our model fit by adding this or these predictors to the model. So here, by adding which university that attendees are employed at, sorry for that grammar, by adding employer, we've done a better job at predicting whether the person has tenure or not. So we're also going to get these additional tests. There's a -2 log likelihood test, which we can use to compare models from one another using a deviance test, and I'll explain that to you probably tomorrow or next week. We get these R-squared values, and they're both very similar to the R-squareds you're used to. They're called pseudo R-squareds, but they're percents of variance accounted for, essentially. You can use them in about the same way. And I didn't say the same way because you need to say which kind you're using, but you use it the same, it answers the same kind of question. All right, now we're at the good stuff. Here we're in the classification table. We get the observed, that's what really happened, and we get the predicted contingency table here. So right here, we have the people who, once I've solved this equation, the people who I think won't get tenure and the people who I think will get tenure. And then I also have observed whether they didn't or did get tenure. So you see that unlike the last one, I've done a little bit of a better job because I have numbers in all of these cells. I had 204 people. I have accurately classified 42% of those who do not have tenure. I've accurately classified 96% of those who do. Overall percentage of 70%. The rest we got wrong. So the on diagonals we got correct. The off diagonals we got wrong. Okay, so here, these are the values that we use to get to this contingency table. We can use this prediction equation here, y hat. Remember, that's our predicted score, which we're going to use to determine whether we think they do or don't have the event happen. Here's the prediction equation for the y hat. So we're going to have, I called it school, but it's like university. Is it Kenyon or is it Ohio State? So I have y hat equals 1 over 1 times e times b0, which I've harvested from here. Bizarrely, check it out here, you guys. The constant in logistic regression gets plopped to the very bottom of your table. So you'll look for it in a different spot than you have before. It'll be the last thing. So here's your constant, your b0, plus b1 times x. So here's b1, 2.79. And so I can, just like we did with our OLS regressions or with our GLMs, you can fill in your predicted, you can fill in your your x values into this equation to get your expected score on y. So here, for Kenyon College, this variable of Ohio State would be 0. So then I plug in a 0 for my x value. This cancels out. And this solves to 0.09. 0.09 is less than our cut point of 0.5. That's a 0. So we're going to guess that all of those folks do not have tenure. For Ohio State, we do need this one. We plug in 1 for the x value, and so then we solve that down to 0.61. 0.61 tells us, again, yes, we have tenure. That's what we're guessing because it's above 0.5. More likely to have tenure than not have tenure. So now let's look at this odds ratio. The odds ratio here is the exponent of the b term, which is kind of cool that that's how that math works out. It's the probability of, for the intercept, which is the constant. The constant is focusing on when x equals 0, just like always. So when x equals 0, the probability that y equals 1 when x is 0 is in the numerator over the probability y equals 0 when x is 0. So this is only talking about those folks who are at Kenyon College, those folks at our event that have purple name tags on. I have the probability of yes, the event happening over the probability that the event did not happen, both of which are contingent on whether that person has a 0 on the x. Probability of t given k. I call that for Kenyon College. Probability of not having tenure given that you're at Kenyon College. So we can solve that, and that gives us 0.103. And we get that right from this contingency table. The probability of having tenure given Kenyon College is tenure Kenyon College 9. See where I got those? Over, and probability is always the thing happening over the total for given that thing. So that's how we end up with these numbers. Okay, now, next. I just did that. What is happening? All right, the slope we're interpreting somewhat differently. For the slope, instead of comparing the event happening over the event not happening, now what we're saying is it's a 1 unit increase in x, which means we're going from Kenyon to Ohio State. So if I'm going to grab 2 random people and one of them has a red name tag and one has a purple name tag, what's the increase in odds? What's my comparison of odds from the person in Kenyon having tenure versus the person at Ohio State having tenure? So it's the ratio of the odds that y equals 1 when x equals 1 over the odds that y equals 1 when x equals 0. So I've increased x by 1 unit. So it's the odds of yes tenure at Ohio State over yes tenure at Kenyon. Da-da-da. And that's a huge number. So if I walk up to a table and there are two people there and one's from Kenyon and one's from Ohio State, I'm much more likely, the odds that the person from Kenyon has tenure are 16 times less than the odds that the person at Ohio State has tenure. So I'm just going to synthesize all of that and put it together into something that's a little bit easier to digest and what you would actually say when you're interpreting this. First, you would say, the chi-square test in block 1 here is telling us that the model with the institution, or model with Ohio State versus Kenyon, fits better than the model that doesn't. My R-squared statistic here is showing me that about 20% of the variance in whether a party attendee has tenure is explained by institution. I'm pulling that number from here. What happened? Okay, our classification table here is showing us that we've correctly classified about 70% of the people at this event. And we did a much better job predicting who would have tenure, where we have 96% correct, versus who would not have tenure, where we're about 42% correct. The exponent b of the constant tells us that if you see someone from Kenyon, they're 1.03 times more likely to have tenure than not have tenure. You can also calculate the inverse, just flip the numbers around, and that folks at Kenyon are almost 10 times more likely to not have tenure than to have tenure. Just to, if that number makes more sense to your brain, you can flip them around. The exponent b of the slope for Ohio State tells us that a party attendee from Ohio State is 16 times more likely to have tenure than a party attendee from Kenyon College. "16 times more likely to have tenure if you're at Ohio State than if you're at Kenyon." Whew. Does your brain hurt? Because I'm going to make you apply it right now with an online Carmen quiz. But I'm going to introduce the Carmen quiz first and give you several minutes to go back through stuff and actually look at it in order to answer these questions. Here we go. Here I have data about students who end up in a remedial math class or in a standard math class. So my research question here is there a gender difference between those students who end up in a remedial math class and those students who end up in a standard math class? In this data set, gender was coded as 0 for male and 1 for female, and they don't have any other gender identities represented. In this data set, remedial math is 1, yes, remedial math, 0 in a standard math class. Here, this is telling me, does the model fit? I have a significant chi-squared test. So that tells me that the model fits the data well. My R-squared is between 2 and 3%. They're pretty small. The log likelihood, I have nothing to compare to. I haven't showed you how to use that, so that was kind of rude of me to put it on this slide. So just ignore that. And so now what I'm going to do is show you more output from block 1. And what I'd like for you to do is go, this thing stopped working. I'd like for you to go to Carmen and into this module for this week. And there's a quiz there where you will answer questions about this output. So you can use the PowerPoint presentation that I've given you today to go back through and help you answer the questions. I'm going to give you 15 minutes to work through as many of the, I think it's 6 or 7 questions, as you can. I'm going to pause this recording and I will come back and we'll discuss the results. Okay, we're here to go over the results of the quiz. And I'm going to start by asking from the groups, can somebody throw out one question that was confusing that you'd like to go over with the group?
Can we talk about number 4?
Yes, we can. Take it away, Lisa.
Yeah, so I had the same question about number 4, and my confusion was that in looking at the table with the variables in the equation, we know that like sex 01, that row is talking about the females, and I assume that like constant would then be talking about males. So I wasn't sure how like constant is talking about the estimate with like regardless of the gender, because that is referring to male, and that's where my confusion was.
I mean, same here, but in the previous example, we interpreted constant as being Kenyan versus not being a Kenyan. So why would we not interpret this as being male?
You absolutely would, and I completely got it wrong.
Okay.
So good work. I don't know what happened in my brain there that I got that completely wrong. So yes, for question 4, I'm just going to go ahead and take it out completely of the quiz because it is completely wrong. This constant is all about males yes versus males no. That's what the constant is comparing. Males yes versus males no. And sex 01 is comparing females yes over males yes. And I'm really sorry because that must have been really confusing, especially because it was really early on in the quiz. Not very good at developing self-efficacy, so I apologize for that. All right, so that's question 4 explained. We're going to get rid of that one. What's another one? I know we have question 7. Does anybody have one other than question 7?
Can you clarify the comparison again for the betas? So you said that the 0.499 means that it's females are 0.499 more likely than males to be in remedial, and then the 0.63 is males are 0.63 more likely to be in remedial than other males.
Then not in remedial.
They're not in remedial. Okay.
Uh-huh.
And are they both compared to overall? Wait, so the first one's females versus males, and the second one is males. Okay.
Males yes in remedial math versus males no, not in remedial math. Females yes in remedial math versus males yes in remedial math. So the constant is always for everything who's 0, because next one we're going to scale it up and add more predictors. Not today. We're done for today after this. Don't worry. But after, it's always when every variable in your predictors is a 0, that's where we're interpreting the constant. Yes for everybody who's 0 versus no for everybody who's 0. For every other thing you'll interpret, all of the slopes are yes versus yes for the people who are scoring a 1 versus yes for the people who are scoring a 0 on this X predictor. Okay, so that's all the ways I was wrong about number 4. So let's talk about number 7 then, since that one comes up a lot as well. So for number 7, I asked you to look at the classification table and use that to talk about how well our model is predicting our data. Several of you pointed out that, hey, the chi-squared was significant, so our model is predicting the data well, which is true, but is not part of the classification table. So within the classification table, there's a couple of different numbers that you can look at. Did anybody feel pretty confident about this and would be willing to explain it in words that are not mine?
I don't know how confident I feel, but I can try. So the math, the computer kind of guessed that all of them are not in a remedial, and so put everyone in there and says we've got 100% of those correct, but it put basically none inside the the remedial course, and we got none of those correct. It screwed that up entirely. And so our overall model that did all this guessing is only 68.8% correct. So 70%, but the fact that it didn't put any inside the remedial courses, which we know there were people, is a problem.
Yeah, excellent. So there's a lot of information there that Hannah just talked about. So we've got, first of all, we got 100% correct here on the non-remedial math. That's a piece of information. But 0% who should have been in remedial math. That's also a piece of information from this table. 68.8% is another piece of information that you can explain from the table. And then the last one is that the computer, using this equation, everybody got an expected cut value below 0.5. So everyone is expected to not be in remedial math, which means our model didn't really do a great job. Like if you were going to try to use this model in an actual school, you couldn't do it because you would end up with nobody predicted to be in remedial math. You need more things. You need more predictors in order to figure out where kids should go. Other clarifications on this wonky table. It's just kind of confusing to read which this is predicted, like these are the predicted values and these are the observed values, and how those align can feel confusing, I know.
Dr. Logan, I have a question about what you said. You said everybody got a cut value below 0.50. How would I infer that information from that table?
Sure. So the way that the computer has done the math, they've taken these numbers, the computer has taken this number here, the 0.695 and 0.460, to create one expected probability for every single person. And so that expected probability for each person, if it's below this cut value of 0.5, then we're going to guess that they're going to get a remedial score of 0. So we're going to guess that they're not in remedial math. And because this right here in remedial, in our predicted remedial, has 0 and 1, I have everybody here in the 0 category. And nobody has been put in this 1 category. This is empty. So that's telling me that the computer has guessed that every single person is not in this remedial math class.
Okay.
Nobody is in the class. That's their guess. So the equation that they use to do that is the one that I explained to you at the beginning in sort of our scaffolding section. But the result of that equation is displayed here in the observed by expected table. Okay, and question 2, many of you got right, but for some reason the computer would not acknowledge that I kept updating the score to be correct. So I apologize about that. Hopefully I'll finish grading all of your quizzes as soon as we hang up today, so you'll have the correct score after that. Okay, other questions on this quiz that I can answer for you? Okay, then here's what I need you to remember is that your homework that's due on Monday the 22nd is your rough draft of the final project. So take a look at the final project and the rubric. And if you have any questions about how to make that work or what you should do, or you have so many questions you don't even know that you have questions, please send me and either get on my calendar or send me an email and we'll meet and talk about it as soon as possible, okay? All right, take a look at that then, guys, and have a lovely rest of your week. You'll learn more about logistic regression tomorrow in lab, and I will see you on Monday, again, online, I think. Yes, again online, if not before. Okay. Happy Monday, everyone.
Thank you.
Yeah.
Bye.